Here are solutions to homework set number 10 for Modern Control 463-663. This homework set looks at designing servo compensators using LQR methods. Now, a servo compensator is where you take your plant, add an integrator to it. What that does is that lets you track a constant set point and reject a constant disturbance. So if there's a disturbance over here, it would reject that as well. When I do that, I get an augmented system. For a fourth order plant like this homework set, I've got 4 poles here, 1 pole there. The net is the fifth order system. Find your 5 feedback gains to stabilize the system. Now, one way to find the feedback gains is pole placement. We looked at that in previous homework sets. In this lecture, or this homework set, we're looking at LQR methods. So the procedure is first, start with the plant, add the servo compensator. When you're done, I get the plant, the augmented system, it's now fifth order, my A, B, C matrix. Now find the feedback gains using LQR methods. The trick I'm going to use is to find the desired response. So this is something that meets my requirements. Settling time of about 6 seconds, less than 10% overshoot. Kind of arbitrary. Here's my dominant poles. These you may or may not need. I just included them because it's a fifth order system. A lot easier making a fifth order system look like a fifth order system. But the procedure with LQR methods is kind of trial and error. So this is just a tool, one way to design your feedback gains. If I go over here, I've got the plant, the desired response, LQR is right here. Here's the weighting on Q and R. R is just 1. If I make the weighting 1 on the servo state, the desired response is in red, actuals in blue. It's too slow. Crank up the gain. Increase Q, I get a faster system. Now the state that I'm looking at right here, this is the weighting on the servo compensator. It's kind of counterintuitive. This is the state that I actually care about, the output. I do not weight that state. Instead I weight the servo. If I were to weight this state, this actually looks like friction. That slows it down, says get there slower and slower. The heavier I weight that, the smaller the derivative of the output. The control law is dumb. It thinks that Z is the output. It thinks that Y, this right here, is the derivative of the output. So the heavier I weight the derivative, the slower I get. So again, I don't actually want to weight the derivative, get the desired response. Here I might have too much overshoot. So one way around that is reduce this gain, or the derivative actually does help in this case. It was too much. Try 20. A little bit subjective. Once you're happy with the response, there's my Q, there's my R. At that point, I'm done. I play around until I get a good response. Eventually wind up with something. Here's my desired response. Here's the actual response. I'm going to say good enough. That's Q. Here's R. And the resulting feedback gains, here's your KX and KZ. When I do that, I've got closed loop holes somewhere. Turns out this is the optimal place to put the closed loop holes given them my cost function. I don't like the word optimal because my cost function is completely arbitrary. It's whatever seemed to make the system behave well. What's neat about LQR is the dominant pole makes sense. I've actually got 3 dominant poles. The other ones, I don't really know where these belong. They drop out automatically. With pole placement, I had a problem because I didn't know where to put the non-dominant poles. With LQR methods, you don't have to worry about it. It drops out anywhere automatically. The real acid test is when you try it on the actual nonlinear system. So here's my simulation of the cart and pendulum system from earlier homework sets. Here's my feedback gains, KX and KZ, found using LQR methods. Seems pretty reasonable. It's working about the way I expect. So really, this is just another way to find your feedback gains, similar to pole placement, just a different technique. Next problem. Look at a ball and beam system. Use LQR methods to try to find the feedback gains for this one. So here the procedure is almost the same as before. I define the plant, the augmented system, plant plus servo compensator, find the feedback gains. Here's the weighting on Q. Start with the weighting on the servo compensator and play with the gains until it's reasonable. So here's my plant where I want the poles to be. Start with weighting on the servo. Try that. Here's the desired response in red, actual in blue, and it's way too slow. So start cranking up the gains, increase the weighting on Q. That speeds it up. Maybe start playing with these gains, see if that helps. Maybe a little bit. Let's try this one. This is on the angle theta. Maybe x dot. Ooh, that was good. I like x dot. Theta dot. I think x dot worked better. So I need to speed it up some. Not bad. Again, there's really no rhyme or reason. It's whatever works. So if I wait 1,000 on the servo state, 600 on x dot, maybe too much. Again, play around with the numbers until the response looks good. Not too bad about that. Okay, once you're happy, you've got your Q, you've got your R. Here, when I played around with it, that's what I wound up with for this response. The net result is you get your feedback gains. Here's the feedback gain times state, Kx. Here's the feedback gain times the servo compensator, Kz. And when I did that, I placed the closed loop poles somewhere. Again, if I did pole placement, I would get the same answer. I would not probably guess this location for pole placement. The power of pole placement is you can put the poles anywhere. The dominant pole kind of makes sense. The other poles, not really sure. LQR, they all drop out. So when you're done, there's your feedback gain. The acid test is try it. So here's my nonlinear simulation of the ball and beam system. There's the feedback gain Kx that I calculated, Kz, the servo state. When I run it, here's my step response. And these gains also work. Meet my requirements pretty well. So really, LQR is just a tool. It's one way to find your feedback gains, similar to pole placement. Some people really like pole placement. Some people really like LQR methods. It's a tool. If it works for you, use it. If it doesn't work, don't use it. Just another way to find the gains. What's nice about LQR is you tend to get reasonable gains. It places all the poles in a reasonable spot, and it's fairly easy to tune. You just play with Q and R until you get a good response. But again, just a way to find the feedback gains. That is homework set number 10 for modern control.